Hello, AP Bio, and welcome. Let's talk about Chapter 5, the cell membrane. So we're going to be exploring a few topics today. The fluid mosaic model of the cell membrane. We're going to be talking about diffusion, osmosis, and movement of substances across the cell membrane. And then we're also going to be talking about water potential. So some really exciting stuff today. Nope. All right. So what is the cell membrane? Well, at its most basic, the cell membrane is the boundary between the cell and the outside environment. So our cell membrane is going to control transport in and out of the cell, as well as intercellular and intracellular communication. And so I mentioned earlier the fluid mosaic model. This was first proposed in 1972, and it's been updated since then, like any good model in science. But it has roughly maintained our understanding of how the cell membrane works. So we're going to watch a short little video.
Between the living machinery of the inner cell and the harsh conditions of the outside world stands the cell's plasma membrane. As crucial as this barrier is, it's surprisingly flexible. Push it and watch it move. Poke hard enough and it might break and begin to regroup. The lipid molecules of the membrane naturally assemble in a double layer because their tails repel water as their heads attract it. Throw in some cholesterol and a few carbohydrates, and you have the basic structure of a plasma membrane. Within these lipid molecules, we also find different proteins which do various things for the cell. For instance, they receive signals from the world outside, or they transport nutrients in waste. So nature composes the membrane with a combination or mosaic of different lipids, carbohydrates, and proteins. And these molecules are not stationary. They constantly move within the structure, fluidly changing their positions. The survival of all life rests on this veil of material. A supple membrane just 2 molecules thick.
So that does a great job of showing you some of those features of the fluid mosaic model and some of the structural components that build it up. But it really is fluid in that it's constantly moving and changing, and all those individual pieces are able to move around one another while still maintaining a barrier that's enough to repel things from entering in between. So what goes into our double layer membrane? Well, phospholipids are the vast majority of it, and those are going to be lipid tails with a phosphate head. There's carbohydrates that are there for cell-to-cell adhesion, so holding cells together. There's glycoproteins, which are proteins with attached to carbohydrates that are there for cell recognition, so knowing cell from other cells. There's proteins, both integral, which means that it goes through the cell membrane. So that's going to be for transport or communication, either sending materials into or out of the cell, or sending chemical signals into the cell. Or peripheral, which means that they're on one side or the other. They don't go through the membrane. And those are for regulating other proteins, and so helping to regulate communication or transport. And finally, there's steroids, mainly cholesterol, and that helps prevent the phospholipids from getting too tight together and keeping it nice and flexible. So let's talk about these phospholipids. These are amphipathic structures. So what does amphipathic mean? Well, this means that they have both a polar region, the head, where the phosphate is, and a non-polar region. And those are going to be those tails. So remember that polar loves water. So they're going to be a hydrophilic head, and nonpolar is hydrophobic. It hates water. So what ends up happening is when you put these in an aqueous or watery solution like the cell, they're going to organize so those tails are together to hide them, and those heads are on the outside because they're loving that water. And these tails also have a double bond. You can see right here that double bond between some of the carbons. If you think back to macromolecules, that's going to be a unsaturated lipid or an unsaturated fat. And that gives it a little bit of a bend. And that bend is going to also prevent it from getting too tightly packed together. If you think about it, when clothes are really nicely neat and folded, really straight and folded, you can pack a lot together. But if you just bunch of clothes in a suitcase, you're not going to fit as much in there. And so this is also going to help with the fluidity of the membrane and allow things to move around. So amphipathic substances, like I mentioned, will clump together in water. And they're going to form either a bilayer, like you can see with our cell membrane, where all those hydrophobic tails hide in the middle, where they can be protected from water, or they'll form something called a micelle, which is kind of a little bubble where everything's protected on the inside where there's no water. This is actually how soap works. And so we can see the hydrophilic regions interact with water, the hydrophobic regions interact with themselves, and hydrophilic on the other side will interact with water, making for a nice protective layer. So like I said, soap is a lipid. I thought I was getting rid of grease and lipids from my hands. Well, it's also a lipid. And what it does is that hydrophilic head is going to approach the water, where the hydrophobic tail will get around those non-polar dirt or greasy substances. And so it'll form a little micelle around those greasy substances. And then water will push along the polar heads and be able to wash away that grease because it gets enveloped by the soap. So when we're talking about what goes on with transportation on either side of the membrane, it's important to remember that nature hates imbalance. Nature loves to spread out, just like you saw in that little GIF there where they're all clumped together and spread out to be nice and spaced out. Nature loves to socially distant. And so everything in nature will naturally flow from an area of high concentration to low concentration. So when everything was packed together here, it's going to spread out to where there was less concentration. And this is called diffusion. So moving from high to low concentration, that's spreading out. Anytime you have an imbalance in concentration on either side of a membrane, so you have more of something on one side than on the other, that's going to be called a concentration gradient. So a gradient is a gradual change in something. So if you've ever seen a color gradient, you see changing from one color to another. Concentration gradient is going to be different concentrations, the same concept. So with this concentration gradient, because of diffusion and the laws of physics, when you have a really high concentration, particles are going to want to move down the concentration gradient, go from high concentration and move to where there's low concentration, because there's more room to spread out. It's easier to move around. If you want to go from a low concentration to a high concentration, you've got to move up the concentration gradient. And that is going to take energy. Anytime you've got to go up a concentration gradient, you got to put in some energy. You got to put in work. If you have a little bug trapped in your hand, that's a high concentration area. If you open your hands to the rest of the world, it's going to fly away. It's going to go towards where there's low concentration. And if you want to get that bug back in your hands, you're going to have to put in some energy to do it. So our membranes are selectively permeable. So what does that mean? Well, some things can go through. Permeate means to go through. So some things go through and some things don't. So small, nonpolar, and uncharged molecules move through the membrane really easily. Remember, if it's nonpolar, it's not going to have a problem going through that nonpolar region of the tails. Additionally, really big things, even if it is polar, is going to have trouble fitting through all those phospholipids. And if it has a charge, that's going to be attracted to polar regions. And so it's going to have a tough time in those non-polar areas. So small particles like oxygen are really, really highly permeable. Low permeability are big things like sugars or ions that have a charge. You may say like, wait, water, that's polar. Why is it able to get through so easily? Well, we're going to talk about that here in just a little bit. So hydrophobic molecules drift right through. Small and uncharged polar molecules can make it through with a little more difficulty. Large molecules, they're getting bounced, and ions, you better believe they're getting bounced. So how do we get these things through? Facilitated diffusion. Facilitated diffusion is molecules that are polar or charged or really big that need to get through the membrane. And so they're going to use some of those integral proteins that are built into the membrane called protein channels. And these channels are going to be specific for specific molecules. You can see different types of channels here, letting things go in and out of the membrane. And these channel proteins are going to move these substances across the cell membrane. They're going to recognize them and move them across. Same thing here, recognize and move across. Channel proteins are going to be very specific. So they have to recognize the particle in order to let them in. For example, sodium channels or magnesium channels are very specific. Only sodium's going to pass through, or only magnesium, or only vitamin B12. You're going to have specific proteins for what you want to get through. Not everything can just flow through. This is going to help the cell keep things out that it doesn't want to come in. So I said, how come water can make it through so easily? Your cells are chock full of little proteins called aquaporins. Now let's think about that word, aquaporin. Well, aqua is going to mean water, and a pore, like the pores in your skin, are openings. So aquaporin, water opening. These are proteins that allow water to flow through. And anytime we're talking about water moving through, because water is so important, it gets its own special word. That's any diffusion of water is going to be called osmosis. Now, these aquaporins are still going to be pushing water down the concentration gradient. So going from a high concentration to a low concentration. So this is going to bring us to, when we're talking about movement of water across a membrane, osmosis, it's going to bring up something called tonicity. So we're going to be talking about 3 types of tonics. Hypertonic, which hyper, like your hyper young nephew or niece, is too much energy, too much. Hypo, like with hypothermia, is too little. And iso, like a one-on-one iso play in basketball, means equal. So tonicity is going to be the relative concentrations of solute, or the dissolved particles in a solution, between 2 solutions on either side of a membrane. So inside the cell and outside the cell. So as I said, hypertonic, hyper means a lot. That's going to be more solute than is on the inside. Hypotonic is less solute. And isotonic is equal concentrations on both sides. Now remember, these terms are comparative. So if you have a hypertonic, which means more solute outside, so more hypertonic solution, more outside, if you put a different item in that solution could become hypotonic because it's just comparative. If you have a lot of sugar in a solution, it could be more concentrated than what's the cell that's sitting in there. But then if you put like a gummy bear in there, maybe that gummy bear is even more sugary than that solution. And so now water is going to move the other way and it becomes a hypotonic solution. Typically, when we talk about the solution, we're talking about outside the membrane. So if I say a hypotonic solution, it's going to be what's outside the cell, not what's inside the cell. If I say isotonic, well, that's both sides. And hypertonic, again, outside the cell. So here's some good images. Hypotonic. too little solute. So you can see the dissolved solute particles are in green. The ratio of how much is outside is way less than what's inside. Isotonic, it's pretty equal. And here, hypertonic, too much, you can see that it's way more outside than is inside. And tonicity is really important in biology. It really affects your physiology. So let's think about your blood cells. Remember, solvent, the water, moves across much easier than the solute. So say you have a lot of sugar in your blood. The sugar is not going to move across as easily as water will. So if you're hypertonic, you have a lot of sugar in your blood, water is going to leave your blood cells and into your bloodstream, into the plasma. And so your blood cells are going to shrivel up. If you have the same amount of sugar or salt in your blood as in the inside of the cell or outside of the cell, it's isotonic, then there's not going to be a real change. The blood cells will stay normal. It is important to note, though, in an isotonic situation, that doesn't mean there's no water flow. It means water is moving into and out of the cell at the same rate. Water is still moving, but it's moving at the same rate. With a hypotonic solution, that means you have so much more sugar in the cells than in the plasma that all that water is going to move into your cells, and your cells can actually swell up and burst. This is what happens with water poisoning. You've heard of maybe if you drink too much water, it can be damaging to you. Well, that's true because your cells will swell up and burst. There's too much water. It's the reason why if you're dehydrated, a hospital won't just give you an IV of pure water, but they're going to give you a saline solution that has some sugar and salts in it, so it creates an isotonic solution for you. It is important to note that these relationships are going to be different for different species. So for us, with no cell wall, it's really clear. We prefer that isotonic environment. But plant cells are actually going to prefer a hypotonic solution because the cell wall applies some pressure. And if you get too much water in the cell, that pressure from the cell wall will actually force water back out. And so then you have energy going in. You have a force or a pressure pushing water out to make sure that plants stay nice and turgid. If you have a hypertonic or an isotonic plant, it's actually going to start to wilt. So now we're talking about pressure being added or going against a concentration gradient, adding energy. This is going to be active transport. We're being active. We're adding energy. So this is where cells are moving molecules up the concentration gradient, against that gradient. And in order to do that, you got to use energy. So energy is going to be used to operate things called protein or pump proteins or protein pumps. These are going to pump molecules against that gradient. And as we said, nature hates imbalance. Things will always move from high to low concentration in passive transport or diffusion. But if we're going to go against that concentration gradient, we need ATP or energy. In fact, you spend most of your ATP or most of your energy on a given day powering one of these sodium and potassium pumps, one of these active transport protein pumps. And this sodium potassium pump, which we'll talk about later when we talk about neurons, is going to move 2 potassium inside your cell and 3 sodium outside your cell to keep these concentration gradients stable. They don't want the concentration gradients balancing out. It wants to keep a gradient. And we'll talk about later why you might want to keep a gradient. So if we're talking about the movement of water and which way water is going to move, we're going to be talking about water potential. So water potential is a measurement of how likely it is water will move either into or out of a solution. So I'd like you to think about 2 people pushing on a door. 2 people are pushing on either side of a door. Which way is that door going to move? Well, whichever side has more pressure being pushed onto it, it's going to push in the opposite direction. So if you have less pressure on one side of the door, a negative pressure, it's going to move towards you. So the more negative the water potential, the more likely water will move into that area. So if you have two sides of a membrane, one side is more negative, water is moving to the more negative side. If you think about it, negative numbers are lower than higher numbers, and so the water will fall down. It'll fall to the more negative side. Think about it like a waterfall. Water will fall to the more negative height. Water will fall to the more negative water potential. Just like a concentration gradient, water is moving from high potential to low potential. And pure water, just stationary, will be assigned a potential of 0. So what's going to affect water potential? Well, two things. Pressure potential, is there any active pressure or force on it? And solute potential, how much solute is dissolved, causing water to move one way or the other. Remember, water moves towards a higher concentration of solute because that's a lower concentration of water or solvent. So this is going to be our basic equation. We're going to use psi here. And I love that we use psi because it's a trident shape, and Neptune, king of the seas, big on water potential, has a trident. And we're going to be using bars, which is a pressure unit, to talk about water pressure. Now, if we just have regular atmospheric pressure, usually our pressure potential is 0. Unless there's something actively pushing on the situation, usually it's going to just be our solute potential on either side of the membrane. So what are some examples of pressure potential? Well, think about like if you had a tube with a membrane in the middle and you had a piston pushing on that water, applying actual pressure, sort of like a super soaker or a pump. That could be pressure potential that changes your equation. Another situation is if we have a cell wall, like a plant cell. That plant cell wall, I said, is applying pressure on the inside. And so even if you have more solute on the inside, it's a hypotonic environment, water could still get pushed out because of the pressure potential of that cell wall. So anytime you have external forces applying pressure, that's going to be that cell wall. Remember, all of this water potential stuff is important for plants. All of transpiration is when you remove water at the top of the leaves out the stomata, that creates a negative water potential, and so water will move up to replace it. So how do we calculate solute potential? Well, we have a little equation. Solute potential equals negative I crit. And hopefully it doesn't make you say I quit. So I is our ionization constant. And that is going to be how many particles does something break into when it's in water. C is the molar concentration. How concentrated is it? R is a constant. You'll always use 0.0831 liter bars per mole K. And T is temperature, and we're always going to be in Kelvin. So Kelvin is a unit based on absolute 0. And how you figure it out is you take degrees Celsius and add 273. Absolute 0 is negative 273 degrees Celsius. And so Kelvin just starts at absolute 0, and the next one up is 1. So just degrees Celsius plus 273 will get you your Kelvin temperature. So what did I mean by ionization constant? Well, things break apart in water. Sugar molecules don't break down any more than, like glucose or fructose won't break down any further than that single sugar molecule. So since it breaks down to one piece, it has an ionization constant of 1. Salt breaks down into sodium and chloride ions. So it breaks down into 2 pieces. So its ionization constant is 2. So however many pieces it breaks down into, and I or the College Board on a test will always give you the ionization constant. So don't worry about memorizing a bunch of those. So let's solve an example problem here. Let's figure out which of the following cells would gain the most water if they were placed into a sample of pure water at the temperature. So it's always at 298 degrees Kelvin. And we have our tonicity. So cell A is 2 molar, cell B is 1 molar, Cell C is 1.5 molar, and we have different solutes. So sucrose is a sugar, salt, NaCl, and glucose, another sugar. So let's use our I-crit equation, negative. Remember, our sucrose has an ionization of constant of 1, a molarity of 2, our constant, 0.0831, we'll use that the whole way down, times our temperature in Kelvin, gives us negative 49.5276. Now, our salt, even though it's half as concentrated as our sucrose, because it has an ionization constant of 2, same temperature, same constant here, we end up with the exact same water potential. And then C, again, 1 for our ionization constant. Now we're at 1.5 molarity. It's going to be a little bit less. So you'll notice if temperature is the same, you're really just looking at your ionization constant and your molarity. But we had different molarities here, so just because one is more concentrated does not mean that it's going to be more water potential. And so we see negative 49, those are both the same. So both A and B will gain more water than C. And we'll do more practice with this. Remember, water potential is just which way the water flows across a membrane, based on pressure from either pushing or water is going to chase a higher concentration of solute, because more solute means less solvent, so less water. So water will go towards where there's less water until there's balance. So you can see here, it may even result in situations like this where the water levels you'd think would flow down because it's more concentrated over here. It's going to find that equilibrium. So key concepts in this video: membrane structure, the fluid mosaic model, understanding phospholipids, and then the carbohydrates and proteins embedded in to give it its fluidity and the things it can do with cell-cell communication. Diffusion, remembering that it's selectively permeable membrane. So that can create concentration gradients where there's more on one side than the other. And so how it gets across is either diffusion, passing through the membrane, facilitated diffusion, going from high to low concentration through a protein, or active transport, going from low to high concentration through a protein. We talked about tonicity, which is based on that concentration gradient, which way will water flow. And remember, that's going to create either a hypotonic, an isotonic, or a hypertonic solution. And finally, we talked about water potential, which way will water flow, and we analyzed the equation to figure out which way water will flow. Those are your 4 big things you should take away from this lecture. Ask me questions if you have them, and have a great rest of your day.